Okay, a quick introduction to polynomial functions. What is a polynomial function first and foremost? Let n be a whole number, and all of these things, a sub n minus 1, those are just coefficients. Those are numbers. Let those be numbers. Then the function defined by y equals. Okay, that's a whole bunch of junk there, right? Y equals a number times x to a power plus another number times x to a smaller power plus another number times x to an even smaller power, all the way down to some number times x plus a constant. That's a polynomial. Y'all don't have to write all that down. It's just right here. I'm just trying to show you that it's a number times x to a power plus a number times x to a power, and you write the powers in decreasing order. That's what makes it a polynomial. Now, what do I want you to get from this? Obviously, the stuff that's in red there. You always write x to the highest power first. And you do that because that's the degree of the polynomial. That highest exponent, x to the n, you say that that polynomial is of degree n. That's the important takeaway. Decreasing powers of x, and the highest power of x is the degree. So let's go look at some examples. Is this function a polynomial? This first one. Do I have a number times x to a power? Yes. And are they decreasing powers of x? Absolutely. So yes, that is a polynomial. Now I should also say that they're decreasing integer powers of x. Because on example B over here, I have y equals 3 square root of x minus 5 over x. Is that going to be a polynomial function? And the answer is no. Now, I could write that as y equals 3x to the 1/2 power minus 5x to the negative 1 power. What do you notice about the powers of x? They're not integers, or they're not whole numbers, I should say. They have to be bigger than or equal to 0. Do I need to pause? Okay. We've already looked at several polynomial functions in the last chapter. We looked at the constant function, which was y equals a number, right? Like y equals 2. So what did that graph look like? It's a line that is, it's a special kind of line, horizontal. That's a polynomial function. It's a constant. Let's go back up here. The constant term is over here, right? So all of these coefficients were 0, so y equals a number is a polynomial function. We looked at the linear function, y equals mx plus b. And depending on where your b is and if your slope was positive, negative, or 0, let's just go like that. That's a polynomial function. Why? Go back and look at your definition. This time we just have this piece, and all of these coefficients are 0. Y equals mx plus b. So a linear function is a polynomial. The one we looked at last time in class, the quadratic. Y equals ax squared plus bx plus c. And it was a parabola. Do you see a number times x squared plus a number times x plus a constant? That's a polynomial function. So now you should see why we use a sub n as the coefficient. Because if we had ax to the n plus bx to the n minus 1 plus cx to the n minus 2, what would happen to the letters out front? We would run out of letters. So instead of calling it a, we call it a sub n because it goes with the x to the n term. Instead of calling it b, we called it a sub n minus 1 because it went with the n minus 1 power. You see where they're getting the coefficient terms, names? All right, so we've already seen three kinds of polynomials. We saw constant functions, linear functions, and quadratic functions. Something to notice, the domain of a polynomial function, what is it? Always. All real numbers. The domain of a polynomial is all reals. Okay, the leading term test. Consider a polynomial given by, this was just a generic polynomial, right? We're wanting to go talk about end behavior. That polynomial is going to look, it's going to act like y equals that. As x goes to infinity or negative infinity, f eventually becomes forever increasing or forever decreasing and will follow the general behavior of y equals a sub n x to the n. That is called what we call a power function. So no matter what the polynomial looks like, let me back up. No matter what the polynomial is, all that junk, it's going to behave like that. All of this stuff does, all that makes it do is have the humps. Remember how I talked at the beginning? An x cubed versus an x cubed with big humps? The big humps come from this stuff. But it still looks generally like an x cubed, right? Okay. So here we go. How do I know what that looks like? We're going to look at the power function right here. Y equals a x to the n. If n is even like an x squared, and your a is positive, the end behavior is going to be up, up. Why? Let's go look at this one. I'm going to scoot it over in the middle. Y equals, let's say, 3x squared. Do you see that n is even? Do you see that a is positive? What does 3x squared look like when you graph it? Doesn't it look like this? Now, all we're concerned with is the end behavior. What are the ends doing? They're going up, up. You see that? So if n is even and a is positive, we say the end behavior is up, up. What if a is negative? For example, y equals negative 3x squared. What does that graph look like? It looks like this, right? The end behavior is going to go down, down. Something to notice. If n is even, so the power, the degree of the polynomial is even, the end behavior is going to be the same. It's either going to be up, up, or down, down. How do I say that? Oop. Even degree polynomial. End behavior is either going to be up, up, if the leading coefficient is positive, or down, down, if the leading coefficient is negative. Okay, let's go talk about what if n is odd. So you have an odd degree polynomial. N is odd. Give me an example that we've talked about as a parent function. Y equals x cubed. Okay, so what if you have y equals x cubed? Do you agree that the number out front, the leading coefficient, is positive? It's positive 1, right?
Yes.
What does x cubed look like? Everybody with your arms, you go like that. Yeah. Okay, end behavior is down, up. Down, up. Okay, what if the leading coefficient is negative? For example, y equals negative x cubed. What did the negative do out front? It flipped it over the x-axis. So what's the end behavior when n is odd and a sub n is negative? It's up, down. So a few examples. I know I didn't leave you much room. Go tell me end behavior. Describe the end behavior. What is the degree of this polynomial? Say it out loud. 9. It's degree 9. It's an odd degree. The leading coefficient is positive. So that's going to look like an x cubed graph. So what's the end behavior of an x cubed graph? Down, up. So we're going to say it like this. Now, in Connect Math on the software, how do you say this? I'm going to tell you this way. This says the limit as x goes to negative infinity, so way out to the left on your graph of your function. What did you tell me you're doing? You're going down. That's negative infinity. Whereas this one, you're talking about the limit as x goes to positive infinity, way out to the right. And what are you doing? You're going up to positive infinity. If you were to go look at your graph, it would look like that, right? As you go out to negative infinity on your x, your y goes to negative infinity. As you go out to positive infinity on the x, the y goes to positive infinity. On the test, I'm good with you saying the end behavior is down, up. Let's do another one. So number 2, y equals 14x to the 7th minus 21x to the 5th plus 3x to the 10th minus 3. You need to rewrite that and put it in decreasing powers of x, right? So 3x to the 10th is the biggest, plus 14x to the 7th minus 21x to the 5th minus 3. Why do you want to write it in decreasing powers of x? Because then you can tell that this is a degree 10. Even degree, leading coefficient is positive, end behavior is up, up. If you were to see it in my math lab, this one would probably want you to say the limit as x goes to negative infinity of the function is what? It's positive infinity. This one on the right, the limit as x goes to positive infinity of the function is infinity. Let's do one more. What about y equals 11 minus x to the 8th? So you're going to want to rewrite it as negative x to the 8th plus 11. This is a degree 8, which is even. Leading coefficient is negative 1. In behavior is down, down. Good. Oh, look, more examples. I didn't know I'd put those on there. All right, example A. What's in behavior? Odd, negative leading coefficient. I will agree. Up, down. B. Y equals negative 3 x to the 4th minus 5x squared plus 4. Even degree, negative leading coefficient. I agree. Down, down. C. Ooh. Gave it to you in factored form. What's the leading coefficient? What's it going to look like? You're going to have a 6/7 x to the 4th, an x squared, and a 3x. Do you agree? What is that? An 18 over 7 x to the 7th? All I did was multiply those. Because when I multiply it all out, that's going to be my very first term. Okay, degree is odd. Leading coefficient is positive. So it's going to go down, up. You lost on that one? How did I get this? Okay. Back it up. If I were to go multiply all this out, if I were to multiply this out, do you see x minus 9 4 times? X to the 4th twice, or x plus 4 twice, and a 3x minus 5, and a 6/7 out front. That's what I need to multiply out. When I multiply everything out, you're going to end up with a 6/7 times x times x times x times x times x times x times 3x. That's how you're going to get the 18 over 7 x to the 7th. And then you're going to have a lot of other stuff after it. But all you need to do to determine the end behavior is that leading coefficient and the highest power of x. 6 times 3. Yep. We're going to talk more about how to do more stuff to these types of polynomials later. Right now, I just need you to be able to find end behavior. If you're stuck on end behavior, you can always go put this where? In your y equals and look at the end behavior. Always.